Okay, so this is what the superposition theorem in circuit analysis is saying. That if we have a circuit or a network of this sort, right, and then you want to find the current in a particular branch or the PDF across a particular branch, what we do is that we check the number of voltage sources that are there or the sources that are there, and then we break down the circuit into, what do you call it, or the network into other network depending on the number of the sources there. So this one, for instance, here, this one circle here, when we look at it, we have two sources, which is this and then this, right? So what we do is that we end up breaking the original circuit into two circuits, which is this right here and this, right? So, and the next thing is that after you do this breakdown, you are supposed to make sure that for a particular case, you consider only one of the voltage sources. So looking at this one, for instance, if this is B, we are considering just one source, we are considering just this, right? So in that particular case, we put that one there, which is right here, we place it there. But then any other voltage sources within the original circuit are short circuited, like what we call internal resistance, right? Which is this right here. You see, this one here has been turned to this, right? Okay. So the next thing we do is that you do the circuit analysis, and then you find the current there, the current provided by this voltage source, and with that you can, and you come to the next one, this one right here, you find the current provided by this, and with that you add. That's how we've enabled them A, B, and C. So basically what this is saying is that you have A being equal to B plus C. Okay, so that's what it's saying. With that in understanding that we've gone through in mind, we will try and solve this. So the main thing the question is asking us to find is to actually find this current here, which is a combo of I1 and I2, right? And then today I'll actually need this one here and right here. Adding them up will give us this, right? So we'll start with this one, this branch right here. Because we have two voltage sources as we discussed, we'll be solving this one. We will get what you call two separate circuits to resolve to get what we are looking for, right? So we'll be starting with a B. So we have B, right? And our aim is to be able to find this I1, because it's B, so we've just labeled it I1, just I1, we're part of the I1, which is from the B, right? I2, you're part of the I2, but for the B, right? So that's why we've labeled them this way. So with that, we look at this and know how to find it. So far, per all our discussion we've done so far, one of the commonest things in applied electricity is that we use this equation, which we are very well aware of, right? And then right now, our aim is to find what part of the current, which is this two here, right? And with this, we'll be able to find this, and we'll be able to find what we're actually looking for, the actual plus I1 and I2, right? So meaning that before we find I2, right, we're able to find the I2 in this section B here, this part B here, we'll need R, right? V is very clear. In this particular case, the V is just this 10 voltage here, right? So we'll go on and then try to find the R. What we do is that for this particular example, try and simplify the circuit. So assuming there are, so this how it will be. So we forget about the current, we only maintain the voltage source and everything. So let's see, something of this sort. So we have our voltage source here. Just doing a rough sketch so we'll be able to follow. These are one resistance, another resistance, another resistance, right? This has to be, we're getting all the, what do you call it, the current direction and everything. So for us to be able to find our effective resistance, as we've done so far, we could clearly see that these two here are in parallel. Why? Because we can move, these two here are in parallel because you can move across them, or you can move a loop through them without passing through any other element, right? So it's very clear that we can move from here to here, right? Without passing through any other element aside these two, right? So it means that this actually, okay, so we have their values, so we use their values. So we saw that this is 2 ohms, right? This is 18 ohms, right? And this is 1 ohm. So clearly we could see that we have a 1 ohm which is in series, right? Because we end up transforming these two here into a parallel circuit 1, so which is basically 1 plus the 18. This is a way to represent it. Parallel, that's parallel to the 2, right? So this is how we go about it. So that will give us 1 plus, once there are two resistors in parallel, product over sum. That is 2, right? And that gives us an effective resistance of 2.8 ohms, right? I just went through this very fast because I feel we've done it already. We've discussed it already. So now that we have our resistance, we have our voltage, which is clearly this resistance. We can find the current, and in this case, what will the current be? The current that we'll try to find here is that because this is the voltage source, right? So let's go to here. If we know the resistance and then we know the voltage source, the next thing we do is to find the current, and the current here will be which one? It will actually be the I1B. Why? Let's see. To be the I1B, because you see the direction. This is general the general convention that the long bar for the cell is a plus, and we have the minus here. Meaning it moves in direction. You won't always see this, but it's good we get it. So meaning that the current will move in this direction, right? So the whole of the current supplied by this voltage here will actually get to pass through this and then come here. Right? So this is the main current coming, but this one is just a part of it because of this circuit here. Because here is we remove the voltage source that was here, meaning that somehow, some way, the main current will be this one, and then somehow, because the direction that we picked due to the conversion is in this way, this one we will check how to find this one later. This one kind of be like a part of this I1B here. This I1B, right? So when we get to trying to find I2B, we get to know that because for this particular B here, sorry, for this particular B circuit, which is part of the original circuit, this one is actually a divided current, right? So we'll get to that. So now let's try and find out I1B. Our I1B, right? I1B will be equal to V on R, right? So let me just write this. And then we know that V to be what 10, and then the R to be what 2.8. So that'll give us an I1B. 2.8. Right, so that's giving us approximately, let's do 4 dp, 5714, and that's in what? Amperes. Unit very important. So now we have this, right? Then again, we are still considering just the B part of the, after we know that we can have two, what do you call it, two divisions or two sections of the original circuit, and we are still looking at this one right here, right? That's why we are on it. So we move on and then try the, how many currents are there? Basically we have this and this, right? We have this and this, which add up to give us this right here, right? So the next thing will be to find the I2B, right? So let's see. Okay. So now, because we haven't just one voltage source, we assume that instead of, let's do this one, instead of the current I2B coming showing the direction that it's moving, we actually try to use a different direction. So basically I1B is here, right? But because there's only one voltage source, which is about here, we can't say that this I2B is moving in that direction. It must come from somewhere, because we are still considering this B part, right? So somewhere it might be like this, meaning that this is the original circuit, which is the I1B, but then when it gets to this junction here, per Thevenin's theorem, that's the theory, per Thevenin's theorem, it splits. When it moves, this current moves from the voltage source here, it gets to this node here, it splits to this and this, right? So basically the current gets into this one, so this current here gets to the 18, and this current here gets to the 2 ohms, right? This current here is what we're trying to find, which is the one I2B. So basically in the opposite direction to what is actually showing in the diagram, right? So this is what we call the current division. As we've discussed this already. So we go on and try to find it. What the current division says is that if you're trying to find a particular current, So let's see, in this case our aim is to find I2B, right? We are saying that the current getting to I2B, or the current passing through that particular branch, which we are seeing is this one right here. So our interest is the I2B we are trying to find is actually this one, right? And which resistance is it getting? Resistor is it getting to? It's actually getting to this ohm here, this 2 ohm here, right? So what the current division rule says is that if you are trying to, or division current division rule says that we are trying to find the current passing through a particular resistor as the opposite one, because let's say the current starts from here, right? When it gets to this junction here, when it gets to this here, it splits to this and this, right? But our interest is in which one? This one right here. So to find the current passing through our interest, we use the other resistance, which is the 18 here. So what we do is I put the 18 here, right? And then the denominator will be the sum of the two, or all the resistance that is passing through, right? So basically this will be 2 here plus 18, right? So our interest is actually to find the current passing through this 2 here, which is this one right here. So we use the opposite, as in the other resistance, which is the 18. Put the 18 as the numerator, and the down will be the sum, right? Then the current division, right? So the part of the current that's going to the 2. So we just do a multiplication here times the actual current that splits to for us to get the current passing through the 2 here. Right? So the actual current is the I1B, which is this, which is 0.5714, right? But then what we said was this, that in the actual diagram the I2B is having this direction, right? But because now we are having just one voltage source, we actually have to turn it to make sure it follows what do you call it, Thevenin's rules, that at node, or at a node when the current gets to a node, split. So this is the only current, the main current, which splits to give us this and this, right? So it should be in the opposite direction. So instead of this direction, we actually have this. That's why we change the direction and make here negative. Let me make it. So now we can find I2B. So let's see. That will be 18 on 2 plus 18, which is 20. The point, right? And that is what the I2B will be. That is a 3.2140 dB, right? 2143 amperes, right? So this is what we have. So meaning that we've actually been able to find all the main current that we need in this particular one. Then it's to be to just add them up to get what we have here. Right? So I1B plus I2B, this will be 3 point. This one should be negative. There should be a negative somewhere. Sorry. So whenever you skip a negative, it becomes a whole new story. So this negative is very important. So that will be 18 on 18 plus 2, right? Times 3.5714. Yeah, so this here is negative. Very important. If you skip it, it's a whole new story. So 3.2143 amperes, right? So this plus 3.5714, and this will give us 0.35714 amperes. So basically, because our main aim from the beginning was to be able to find the current in this branch here, right? Which says the combination of this and this, and we've split it. We are done with the B part, right? The next will be to deal with the A part, sorry, the C part, right? So as we said, because there are two voltage sources, we have this and then this. So now we are done with this. We move on to this one, which is the C. Right? So let's see what we can do with it. The same procedure. If you get understand, you can actually skip this part and then get to a part where we do the, what do you call it, the end, where we add up everything to see what we are getting. Right? So now we are done with this one. We're doing the same thing with the C part after we've broken down the original circuit to 2, right, because of the voltage sources. When looking at the C part, this is what we'll do. This is how it will be. We basically have our loads 1, 2, 3, right? We have our voltage source here. Long short. This right here, this right. Okay. So we look at the direction of the current. Then again, because we have the voltage source only here, what this will mean is that the current will be from here, right? The same current being here, right? This side, so this is down. This side is still down, but then because the main current is coming from only just this one voltage source, when it gets here, actually splits to this and then this. What this will mean is that this one here will change direction, meaning you have to put some negative somewhere. So clearly, let's go ahead and do the calculation. So we have our V, which is the 20 volts. Our R will find, and then we will help us find our I, right? And because of how this particular configuration is, our R will be different. One might think it should be the same as the one above, but it's different. So this how to be. You can clearly see that these two resistors here are in parallel. Why? Because you can move across them without passing through any other element. Are you okay? And then the other resistor, the other load, be in series with the rest. Right? So this one right here will be in series. This one here will be in series with the parallel of this and this. Okay. So what this will mean is that resistance, effective resistance. Let me qualify this in C. So this one right here should have been effective resistance in B. Right? Okay. Better. Effective resistance in C will be equal to the one in series is the 2, right? And the ones in parallel will be 1 and 18, right? You can go ahead and find this one, which we see. That'll be 2 plus 1 product over sum on 1 plus 18. And that gives us about 2.9474 ohms, right? Okay, so we have V, we have R, we can find our I. In this case, which will be the I that we are trying to find, because the voltage source is here, right? The voltage source is this one right here, meaning that the voltage source, the only voltage source in C is this one right here, meaning the current that we'll be finding first will be this 1,2C, I2C, sorry. So our I2C V on R, our V is 20, our R is 2.9474, and our I2C this. So let's do that. And basically 20 on 2.9474, and that gives us about 6. I2C be 6.7856 amperes, right? And now that we have this, the next thing will be to find this current right here, current division. So, and that's I. Let's see, I1C. So I1C, we said clearly that to be as a result of current division, right? And then because we haven't just one voltage source, so to be in the opposite direction to what we are seeing, right? To be in this way. So first of all, we have our negative, right? The first thing we do, right? And it's a divided current, right? If it's a divided current, the current division rule, we actually use this one here at the top as the numerator, which is 18, right? We'll do sum at the bottom, which is 18 plus 1. And then the current that we actually divide in is this 1,2C here, which is 6, 5, 6 points. Yeah, this we have. So this will give us minus first 18 on 18 plus 1, right? And this is what's given us. So we get our I1C to be 3.0451 amperes, right? So now that we have these two, we can go on and then find this here. Let's see. This one right here. The current passing through this side, which is the sum of the two currents, right? Which we just found. So I2C plus I1C to give us that. So this would be minus, very important. Minus, let me write this. So that's minus 18 on 18 plus 1, right? Times 6.7856, right? 18 plus 1 times 6.7856. I'm trying to get sure we are on the right path. Yeah, that's what we should get. I think there was a mistake of what we did. That will give us minus, very important, 6.42845 approximately. Amperes, right? So adding this up to the I1C to the I2C, just 6 point, this right here, 7856. That gives us this, which is 3.5713 amperes. So now that we have these two, we can actually move on and find the one we need from the actual thing. Let's try and add this up. So that's 6.7856, right? Minus 6.4285, right? Yeah, this how it should be. Yeah, because we added these two. So that gives us 0.3571 amperes. Right. So now that we have this two, this and then this, we can actually find in the original current this one right here, this here. Right. So what we did was that we split the circuit into two. Right. Let's do a brief summary. We split the current into two because two voltage sources. We found this, and then this helped us to find this. Right? We found this and this, and C help us find this. And now we add up these two here, right? And because our aim is to find this, help us to actually find this one right here, which is our final destination. So this combine them help us to find this one right here. So now we just add these two up. Okay, so we have 0.35714 plus 0.3571. So that will give us a, what's the name? Looking at the diagram, this actual I1. So what we just computed will give us this one, I1 plus I2. So this means I1 from the original circuit plus I2 is 0.71424, right? But let's see I1. Our I1 here will actually be the sum of some other things. Our I2, okay, so our I1 here will mean this I1 here will mean adding this I1 here and this I1 here. So let's see. I1B is 3.5714. Then I1C, okay, is minus 6.4285, right? And that gives us a minus, this is our I1, right? A minus 2.8571, right? And now I2, we are some of the I2s, right? I2B is minus 0. This one right here, 2143 plus I2C is 6.7856, and that gives us 3.5, this amperes, 0.5713 amperes, right? So this is what we have, I1, I2. But our main aim was to find these two, and even when we add this I1 and I2, we add them directly, you see that it actually gives us what we have right here. So let's see, 0. This is that plus, let's see, 0.5713 plus, which is a minus, so minus 2.8571. Yeah, and that gives us what we had at top by just adding the small parts. The same thing. So what we are looking for was I1 plus I2, right? It gives us 0.7142 amperes, which is the same as this one we had here, right? Yeah, so that's it. Superposition theorem, second analysis, circuit analysis. All right.